Hi, and welcome to this lecture about music and samples. So we're going to use the audio and sound knowledge you gained last week, learning about what sound is and how to make tones. And we're going to try and do a bit something a bit more musical. We're also going to play some samples. So quick overview, we're going to look at frequency modulation synthesis, which is a more interesting version of normal synthesis. We can make quite a lot of different tones with frequency modulation synthesis. We're going to look at sample playback, which is going to play back simple sounds. We're going to pan some sounds, so we got stereo, and we're going to look at simple musical ideas as well, like scales. So frequency modulation synthesis is basically the idea that instead of playing a single sine tone of one particular frequency, we modulate that frequency with a separate oscillator. So we have the carrier frequency, that's our base frequency, that's the tone we want to make. And then we modulate that frequency with another oscillator being added to the carrier frequency. So for argument's sake, it might be a 20 Hertz carrier frequency, and we add 1, making it 21 Hertz, and then subtract 1, making it 19 Hertz, because an oscillator goes up to 1 and back down to -1. And that's the input we pass to our oscillator, so it's constantly changing its frequency. It's constantly going up and down in its frequency, backwards and forwards. So that's frequency modulation. So let's have a try at that. Here we've got frequency modulation synthesis, and we have a frequency modulator, and we have a carrier frequency there. So the frequency modulator is a normal sine oscillator with a frequency of 50 Hertz. So that's going to go up to 1, down to -1, and back 50 times a second. The function here is where the action happens. So we take that oscillation in and we do a calculation. This happens every single sample. So every single sample, we're taking that value of that oscillator. It might be 1, it might be -1, it might be 0. And we're multiplying that by 100 and then adding that to the carrier frequency 600. The carrier frequency is the frequency we're trying to make, but we're constantly moving backwards and forwards around that frequency, going up to possibly 700 if the frequency modulator is set at 1, and down to -1, so that would be -100 plus 600 is 500. So the sound is going backwards and forwards between a sine tone of 500 Hertz and up to 700 and back down. So let's have a listen. So you can hear, because it's happening so fast, we can't really hear what's going on. So let's change that frequency of that modulator to 3 Hertz. And you can hear now there's 3 cycles of that wave every second. You can also kind of see that the wavelength is expanding and contracting as that frequency goes up and down. Now this value here, this 100, could be changed to a smaller value. Now here you can just hear a very small change in frequency, or it could be changed to a much larger value, say 300. Now it starts to sound a bit like a siren. And listen to what happens as we speed up the frequency modulator. So here you can hear it's still happening quite fast. But as we go to, say, 10, we stop hearing the cycles. It's very fast now. Sort of sounds like a sci-fi laser gun or something. And if we go up to 30 Hertz, it just about disappears completely. And 50 Hertz, like it was before, it's becoming part of the sound slowly. So this function here is created on the fly, and we can create functions with multiple ugens and treat them with each of these values here. x0, x1, x2 is the current value of each of those ugens. And then this whole thing here is a new ugen we can use in the following chain. So this is used here in the oscillator, the carrier oscillator that is used to create the sound, and that's all just connected up as it was before. So that's just the fundamental idea of frequency modulation synthesis, but there's a few more parameters which make it much more useful. So harmonicity ratio is one of those parameters, and harmonicity ratios can be regular intervals for harmonic tones or non-integers for inharmonic tones. So the ratio is between the carrier frequency and the modulation frequency, and you can say multiply the carrier frequency by 1 and you get the same frequency for modulation frequency there. Or you can multiply it by 2 and you get double the carrier frequency. You can have harmonicity ratios of 1, 2, 3, 4, and you'll end up with regular tones that sound like normal harmonic tones. But if you use a non-integer value, a decimal point value like 1.4 for instance, you'll end up with inharmonic tones. The tone's harmonics won't be related to the carrier frequency in an orderly fashion, and so what will happen is that you'll end up with bell sounds or odd sounds, drum sounds, or sounds like anything that is circular rather than one-dimensional. So strings have harmonic tones, pipes have harmonic tones, but drums, where the sound goes across the drum head, the circular drum head, or bells, where the sound goes around the bell, they make inharmonic tones. Let's have a listen. So here we've got the same old system, but I'm going to open an example that's a little bit more complicated. Here we have FM with parameters, and I can show you the note here has a harmonicity ratio, a center frequency, carrier frequency of 220 Hertz, and a modulation index of, let's start at 1. Now here we'll end up with, I'm going to take the modulation index out, it's not going to change over time, it's just going to be 1 the whole time. So then we're going to end up with and notice we have an envelope, a gain envelope set up to go up to 0.5 and back down to 0. That's fine. Now if I change the modulation index to 2, I get tones with a bit more harmonics in them. Now if I change this to 1.44, what happens? So that's a very heavy bell-like tone. And maybe you can hear it a bit better if I make the carrier frequency higher. And you can mess around with different values there to get different types of tones. Similarly, the modulation index determines how much of the modulation frequency goes into the carrier frequency, so to speak. So you have a harmonicity ratio which sets a modulation frequency, and you also have a modulation index which sets how much of the modulation frequency the oscillator is multiplied by. So you can basically say we're going to start with a small modulation index, and we're only going to get small changes in the frequency. And as you get a larger modulation index, you end up with a greater amount of that modulation frequency being applied to that carrier frequency. So a low modulation index will end up with only very small changes in the carrier frequency, while a large modulation index will end up with very large changes and a lot more complexity in the tone. So the modulation index determines the amount of harmonic content and thus the dullness or brightness of the tone. So just to follow up on that functions section, a function is a eugen that takes as many eugen arguments as you wish, and then you override the calculate method, specifying x0 for the first eugen, x1 for the second eugen, and x2 for the third eugen. And calculate is calculated every single sample, so you can do quite low-level things with this this eugen. Once you've created it, you can use it as an input to something else, like a gain or an envelope, as you wish. So basically, a function is a very flexible eugen that you can use for doing quite complicated things. Now, one thing that we might want to do is use an ADSR envelope to control the modulation index. So here we've got our normal setup for frequency modulation, but instead of just a single value for modulation index, we've got an attack, decay, sustain, release envelope to control the index. So it might go from 0 up to 1 down to 0.2 back. So we've covered ADSR being applied to gain, and that works as well, that's fine, but we can also apply ADSR envelopes to filter frequencies and modulation indexes as well. So that's under, so here we go, we have a note, we have our modulation index envelope, and we're going to set that to 0 to start with, and then we're going to take all this stuff away, and you'll see when we play that, you can hear the sound dying away towards the end. We can make this quite fast. You can hear it gives more of a strong tone to it. I can switch this back to a regular harmonicity ratio. And it gives a harsh start to the tone that is pretty common when you pluck strings or hit chimes or something like that. It's good for making percussive sounds. You can fiddle around with all of these values to get very different types of sounds. So a low frequency oscillator is another form of frequency modulation. Well, it can be used as a frequency modulator, or it can be used passed to other parts of the system. In this case, we're using it to control gain. So here we have a normal frequency envelope passed to a wave player. So we're setting a 500 Hz tone. And we're going to have a low frequency oscillator controlling a gain to add tremolo. 3 cycles per second. 3 Hz. Very slow. Low frequency oscillators usually between about 1 and 10 Hz. more likely to be between 3 and 5 Hertz. So here we have a gain called LFO gain, and the LFO oscillator is the input to the gain. And then we have another gain just for volume control, and we add the sine wave into the LFO, then the LFO into the volume control gain, and the gain into the output, and start it. So let's have a listen to that. Just have to find it. Here it is. So this is the... So there you go. You can hear it say fairly fast oscillation. Now we can make it slower this way. Why are you getting 2 cycles per second? Well, this is an oscillator and it's going up to 1 and then back down to -1, and the -1 is being multiplied. One thing you can do is multiply this LFO by 0.5 and then add 0.5 and make it a LFO only between 0 and 1, but that's not really necessary. As you can see, it works.